Since some of you are doing the projects with caustics, I want to talk about refraction to start with. That's a little bit separate from the syllabus, and then I'll continue with what's on the syllabus. So the idea is the index of refraction should be an N. Is the speed of light in the so this is speed of light in the vacuum is c, and v is the speed of light in the medium, like glass or water or metal or whatever it is, and I'm using eta for the index of refraction. So what we're going to assume is that we have medium, the book calls it medium 1, but I'm just going to assume that this is the incoming ray. And so I'm going to call this theta I, and then when it refracts, say this, if this medium is denser than air, say this is air and this is glass, it's going to refract closer to the normal. So the theta R is less than theta I. And the way to understand it is to think of a wave train of parallel rays. So in the plane of the blackboard, I'm going to draw the normal N. Well, I guess I could have put it on the previous drawing, but let me draw it here too. Here is the surface, and this is the normal N to the surface, pointing, say, toward the incident direction. And here is my incoming beam, say, angle theta I, and refracting to angle theta R. And what I want to do is consider a whole wave train. So I'm going to consider my these lines represent, say, the maximum electric field at a given instant. Right? The electric field is traveling along the wave here, and I'm assuming that this thing hits and then comes out with these lines of constant maximum electric field like this, and they're closer together because it's traveling slower in this medium. So if I look at say this L here, and actually probably I have another one here but I just want to consider this triangle and this triangle. This is perpendicular to the surface, and the wave fronts are perpendicular to the direction of propagation, so this angle is also theta I. And if this is L, the hypotenuse, then this is L sine theta I. And similarly, here is theta R here. It's the same as the angle between the boundary and these wave trains, theta R. So this length is L sine theta R. And the idea is, in the time it took between this part of the wavefront hitting and that part of the wavefront hitting, it went this far in the less dense medium, the incident medium, and this far in the refractant medium in the same time. So we can say this is V in the incident medium times time, and this is V in the refracting medium times time. And that means, I guess, if I take, say, sine theta, L sine theta R I guess I can take the ratio and say that ratio is 1. Sine theta r over let's see, velocity in the refracted medium times time. So sine times L over V, no, L over T. How do I want to do it? I want, yeah, VR here and T over here. And that's the same as sine theta I Li over VI T. This L cancels. Okay, and so I guess I could have probably saved steps if I just wrote it like this. Sine theta r over sine theta I is the same as the thing in the other direction. Let's see, VR over VI. Right? Because this length is proportional to the velocity. But because of this definition, I can see eta in the incident medium is C over VI, and eta in the refracted medium is C over VR. If I want to write it in terms of indices of refraction, it's going to be the other way around. Eta I over eta R. So if eta R has a bigger index of refraction, it's going slower there, this ratio will be less than 1, and this angle will be less than that angle, which is the way I drew it in this picture. So in practice, what we have is a unit vector. Maybe I'll draw it just as a simpler picture here. Here is my unit vector in the normal direction. Here is my unit vector L from toward the light, and here is my unit vector T, which is the refracted direction. And I want to use this law of refraction to tell you how you can actually get a formula for T. So the idea is I need to represent, first of all, this plane of incidence. I guess the idea is I can make another direction here which is perpendicular to n in the plane containing n and L. And then T is going to have, L has components in that plane, and so does T. And I'll try and find the components of T in terms of the components of L. So this length is L dot n, because they're both unit vectors. Let's see. What I can think of is T, if this is theta r, T is cosine theta r times, I don't know, why don't I call this a unit vector u, plus sine, no, let's see which one it is. It's sine theta r times that unit vector u. As usual, I'm looking at my notes that I thought I understood last time, and I'm trying to see what I'm doing here. Cosine theta r times minus n, I guess, because n was up, and this cosine theta r is going down here. So this is minus n, and it's cosine theta r times minus n. And then I have sine theta r Okay, but it's in the other direction, so it really should be minus. I see what I'm doing in my notes. This length, the absolute value anyway, is sine of theta I, right? Because this is a unit vector. This is theta I here, and that's theta I here. So the length of this projection is sine theta I. And what I need to do is figure out what this unit vector is, and I guess what it is if, I'm sorry, I did this wrong. That length is, if theta I is here, this length is L dot n, right? Because this is the angle theta I, and that's the side adjacent. And this is sine theta I. And the way we can figure out a vector, at least in this direction, is to take L minus this. So maybe it's not a unit vector, but let me just say some vector in that direction is going to be L minus L dot n times n. Right? L dot n times n is this vector, and if we subtract it, we'll get this vector. Okay, and so that would give you this vector, and now what I want to do is make it unit length. So I can divide by its length, which is sine theta I, and now because I'm going in the other direction, I have to multiply sine theta r times minus this value. Let's see, what is that going to give me? You think about this. Well, I don't want two minuses. I already have the minus here. I'm subtracting because I'm changing something going in this direction to go that direction. So I made double minuses. Okay, so if I write this formula for that u, I'm going to have cosine theta r times minus n minus sine theta r over sine theta I times L minus L dot n. Okay, and this sine theta r over sine theta I is eta I over eta r. So let me write this minus eta I over eta, it's supposed to be eta r times L minus L dot n. So to get the formula in the book, it's just a matter of grouping the terms. So basically what I have is, let's see, this thing is also cosine of theta I. So, and this is minus cosine theta r of n. So what's multiplying n? It's these two minus signs cancel, and I have eta I over eta r times cosine theta I, and then I have a minus cosine of theta r. That's what multiplies n. And then I have now a minus without a canceling minus, eta I over eta r times L. So that's a formula if you wanted to compute cosine of theta r, but you can compute cosine of theta r in terms of sine of theta r, because this is the square root of 1 minus sine squared theta r. And so let's see, if I put that in, what do I have? I have minus eta I over eta r times L, and then I have plus eta I over eta r, and I'll put this n dot L back in here because that's something you can compute directly without any trig. And then the other thing that multiplies n is this term, which is the square root of 1 minus sine squared theta r. And if you solve that equation for sine theta r, you'll get eta I over eta r times the cosine of theta r, which was which times, let's see, I guess it's got to be 1 minus the cosine squared for the sine. Let's see, n dot L, that's 1 minus cosine squared is sine squared, and the square root of 1 minus sine squared is the cosine of theta r. So this is what multiplies n. So by revising this formula to look like that, now all we have is this dot product and the etas. And so maybe that's an easier way to compute it in practice than doing this trig and these inverse trig functions, a cosine of what the sine was that you found from that formula. Okay, so one thing we have to worry about is if we solve this equation, sine theta r equals, what did I say, eta I over eta r times sine theta I, it could be that this, if you were actually going from a denser medium to a less dense medium, so this ratio was bigger than 1, and you had an angle whose sine was close to 1, the answer would be a number which was bigger than 1, and there's no angle which has that sign. And in that case, it means you have total internal reflection. Say you're going out, as this direction gets closer and closer to the normal, this direction, let me think about that. No, as it gets farther away from the normal, its sign is going to be bigger. Maybe I need to make a picture here. Here's dense, and here's less dense. And the normal ray goes like this. As you go this way, it gets bent away from the normal. It's going to less dense. And finally, you'll get to an angle that it just bends horizontal. And beyond that angle, this is the critical angle when it goes horizontal, there can't be a refraction. And what it means is if you're bigger than this, there's not going to be any refraction. It's going to be totally internally reflected. I say internal because, this could be a droplet of rain in the air or a glass ball that the ray somehow got in, and then the way it hit the other, refracted against another boundary, it couldn't get back out. It bounces around inside the glass or inside the water droplet. And so if your angle of incidence is greater than that critical angle for the material, and you're coming from this dense material into less dense material, or into a vacuum, say, then it's going to be totally reflected. So if you've ever gone underwater and opened your eyes and looked up at the surface of a swimming pool or something, you can see the sky and a certain circle around you, and beyond that you just see reflections off the water to what's under the water, because it's totally internally reflected. So I still have to say, if you don't have this critical angle, so that there is some refracted ray and some reflected ray, how much is reflected and how much is refracted? And that's Fresnel's law. So maybe I'll do that on this board. And the idea is, if you have incident ray coming in, it depends on the polarization. The electric field variation, the electric field can either be in this plane of incidence, which is called parallel polarization with respect to this circle, or perpendicular to the plane of incidence. It's got to be perpendicular to the direction of flow anyway. And so there are two cases, and the formulas are different. Different amounts of reflection and refraction depending on those two cases. So first I'm going to give you the R parallel, which is how you find out the amplitude of the electric variation field is eta R cosine theta I minus eta I cosine theta R over eta. This is the formula in the book, except that they use 1 and 2 instead of incidence and refraction. And R perpendicular is eta I cosine theta I. See, here the I's and R's are switched, and in this form they're not. And then the same formula is with pluses here. Okay, so this is the field vector, but it turns out the energy of an electromagnetic wave is proportional to the square of that field vector. So actually the energy reflected in a parallel ray is R parallel squared, and for the perpendicular, R perpendicular squared. And if you don't know the polarization, you might as well just assume it's half and half. It's sort of like the average of these two reflections. And so if you compute this formula, in the book they might have already squared these, I don't remember. But in any case, you have to compute the average of the squares of these two quotients here, and that's the refracted. Let's see, this is reflected fraction of the flux, which is measured by power. And that means, so if we call this, say, rho, then the transmitted fraction is 1 minus rho, assuming that nothing is absorbed at the surface. So one of the effects, and I'd have to think about it, I didn't think about it ahead of time, so I'm probably not going to try and figure out that, but if you have normal incidence, cosine theta I is 1, and cosine theta R is 1, and so these formulas are going to become much simpler. And if you have glancing incidence, even coming from a less dense medium like air into glass, the amount of reflected gets very high, and the amount refracted into here is less. So you know, you look at a mirror, a glass shop window head on, you can see inside the window, but when you look at an angle, you can see more of what's reflected in the street or whatever. And that follows from these formulas if you think about what happens as this theta I, cosine of theta I goes close to 0. I don't know, I have to think about what it means, but I haven't. So I just know it follows from this formula. So basically, this is the fraction reflected, and this is the fraction refracted or transmitted through the surface. And you can use that. First of all, that's part of the Torrance-Sparrow model for reflections off of a surface. You know, we talked about the rough facets, but they also had the Fresnel effect of the medium. Actually, if it's metal, it has a complex index of refraction, and it's a little more complicated than what I've shown here. Okay, so that's both this formula here is called Snell's law. Knowing the indices of refraction, it tells you how to figure out the refracted direction, and then Fresnel's law tells you how to figure out how much power is refracted and how much is reflected. So now I can go back to what I'm catching up on, which is these other methods of combining radiosity and ray tracing, like path tracing or distributed ray tracing or something. So for radiosity, advantages, no noise, and you can render from any viewpoint. Right, after you've computed the radiosity solution, you can sort of move your camera around it. But the disadvantages it's biased in the sense that once, if you take a specific way of subdivision, you're forced to follow, you know, what basis functions you can get from the subdivision, and so even, you know, if you solve those linear equations perfectly, it's biased into what you can actually show by the way that you did the subdivision. And it has discontinuities where you don't want them if you do patched bases. If you have piecewise constant on a patch, you'll have you know, sharp boundaries between the different patches, even though the light is supposed to be changing continuously. Or if you do linear interpolation, you'll have Mach bands. How many people know what Mach bands are? It's an artifact of Gouraud shading. If you have Gouraud shading across the scan line, your intensity will be piecewise linear. So if this is the direction of the scan line and this is the intensity, you'll have things like that, right? One polygon and the next polygon. And it turns out that your eye has contrast enhancement circuits. Basically, in your retina, a rod or a cone will suppress those adjacent to it. So if a region is brighter, the cones next to it will be less sensitive because of this inhibition. It's called lateral inhibition. And that means this, because your eye is, when it recognizes shapes, it needs to form the outline, the contour. And these are sort of contrast enhancement circuits, in the sense that if we have a change in brightness, say between here, this level and this level. Well, at this level, all these inhibitions will be the same. So you'll have some sort of constant. I mean, one is incoming light and the other scale is actually electrical activity going to the nerve to the brain. But I'm going to draw them on the same scale. And I'm going to draw them according to the fact that this suppression, or maybe I should draw a different graph. Why don't I draw it like this? You know, because I'm measuring something different. And here, I'd be measuring something different too. I'd be measuring the average level here. But this one is brighter. So the effect is that right next to here, we're going to have more inhibition. So this curve is going to go down. And then similarly up here, compared to the average of the inhibition from these neighbors, the inhibition near this edge is going to be less because this neighbor has got less light. And so that's going to make it more. So it's going to give a sort of an enhanced edge effect. It's like it's amplifying that edge, making it easier to see. Well, that's true even here. Here, it's sort of as if the output were the same, as if it were constant, because here it's more inhibition, but here it's less inhibition. So along any of these straight pieces, maybe I'll draw it on a different scale, you have something that's sort of like that. But if you consider, in order for it to continue like this inhibition would have to balance that inhibition, but it doesn't because it's less here. It's continuous, but it's not smooth, so we're still going to get an extra amplification here. And similarly, this inhibition from here is less than it would be if it were continuing straight. So it's going to be higher on this end here too, before it goes down to what it would have been seeing this one. So we also get enhanced edges at discontinuities. Actually, I guess it's going to be even discontinuous here, right, because of that amplification from the lateral inhibition. And that means that you actually see brighter regions perceived at these corners. And these are the Mach bands. And if you look at a gauche shaded picture where there are not enough polygons to represent the smooth surface, you'll see those corners. You'll see the bright areas which reveal the polygon outlines even though it's smoothly shaded. And so that's what Mach bands are. So how about path tracing? Maybe I just point to these things. In path tracing, you've got noise. And you've created it for a specific view because you've traced paths only for those pixels. But on the other hand, it's not biased. And you'll see noise, but you won't see these discontinuities because it's going to converge eventually to the true solution. So what we want to do is combine the best of both methods. And the basic idea is final gathering. And that says you do the kind of recursive ray tracing that's summarized. I keep referring to this page 142 in the book because that's where I told you to look for how to organize your homework. But you don't do more than one bounce for the indirect illumination. Instead, you pick up the color after the first bounce off a diffuse surface, pick up the color from a radiosity approximation. So let L tilde of x be radiosity approximate solution. So you solve either the piecewise constant or at the end of the period before the test, I guess it was a week ago, I talked about actually doing the radiosity solution for consistency of piecewise linear. Or you could do piecewise constant and then average at the vertex and interpolate over triangles. So whatever it is, it's a piecewise constant approximation, and then we're going to do one bounce. So that means this is LEX plus the integral over the hemisphere above x of the bidirectional refraction function. It may be for a diffuse surface, it might just be constant. And then you're going to do L tilde at the point where the ray of x, starting with x in direction psi, hits the surface. And I guess it's coming out in direction minus psi, and then we're multiplied by cosine of nx psi d omega psi. So it's this integral over the hemisphere, but the thing it's integrating, you're not going to do extra bounces. You're just going to, we're going to sample this by Monte Carlo, bunch of different samples, or maybe one sample for a bunch of subpixel anti-aliasing samples. But we're just going to go out to the first surface here, after the one that you're actually rendering, and then pick up the radiosity solution. Well, that'll give you all the color bleeding effects, and it will have some noise in it. In fact, to avoid the noise, you probably still want to separate it into emitted part of this solution, L tilde, and reflected part of this solution, L tilde, and sample separately toward the light sources with shadow rays based on the area of the light sources, and then the indirect illumination would only include the reflected part of this radiosity. So it's the same algorithm, except that you don't have to do it recursively, which is a savings. And it'll still be a better answer than just the radiosity solution. One of the things that I didn't mention is shadow leaks and light leaks. And the idea there is, suppose you have, here's a room with a door in it, and the door is a little bit open. And there is a light maybe in this room. This is maybe a top view. And we've gridded the room like this. So most of this quadrilateral has light on it. So that means when you shade this region, even though it's to the wrong side of the door, you'll see the light leaking through. This room might be dark, have the light turned off, but a light leak. Or in the other way around, if this light was inside this room instead, and you were drawing this room, this would be darker than it should be because of, how can I say it now? This part in this room would be darker because we're averaging the radiosity over an area, and this area includes part of the dark room, so that would be a shadow leak. And so unless, and it's very difficult to pre-compute all the shadows and mesh it exactly to compensate for all the shadows. If you could, that would give you a better radiosity picture, and that's called discontinuity meshing. But unless you take that trouble, and of course then once you open the door a little bit, you'd have to remesh, you're going to get these light and shadow leaks. Well, you won't get that in the final gather. Or at least it won't be as bad because, you know, when you start for a point on this surface, you're going to, the rays you're going to trace for the direct illumination will actually get the direct illumination, and the other rays will get indirect illumination from this room if you were on this side of the door. So this final gathering won't have that problem either. Now, we could do an area form for this. The same, I don't know if, did I write it on this page? It's the same transformation from areas. So this is the angle formula. And we also have an area formula. Area, A-R-E-A formula, which says L of x equals LE of x plus, let me take the FR of x, let me assume it's diffuse, that's what the book does at this point. The sum over the surfaces J of the integral of Sj, these could be your patches in your radiosity solution of your L tilde y, it actually might be constant per patch, times G of x, y, V of x, y, day. So this is, remember we transformed this integral into this integral by figuring out the solid angle of corresponding to this in terms of some cosines in this. What I'm going to do is put a pi in front of this and a pi in the denominator here. Because now this contribution of each surface I is pi times FR times the form factor Fij. If x lies on patch I, this is part of the integral, right? If we take this outside, let me take this outside the integral. L of y tilde times the integral Sj. We'd integrate this over AI and Aj. But if you assume that it doesn't vary too much as x varies in its patch, this is this Fij times Lj, the radiosity at the jth patch. So in a sense, the final gather is like doing this at every point. To say how much all the other radiosities affect the given one. In fact, if you want it exactly at x, one thing you could do is just render the scene from the point of view of x onto the 6 faces of a hemicube at x and actually get the colors of your interpolated radiosity solution as they contribute to x. Right? Then you wouldn't have to say it's the same at every point on the patch that x is on. And so you'd be actually computing the infinitesimal area or point to finite area form factors from x to every other patch. And then just weighting them by the radiosity of that patch. Now, one way you could do it more easily, since you have a single point, is to do it analytically. So that's something that our book doesn't talk about. And what I want to, and I do want to talk about it, is suppose you have a polygon, and here you have a point here and a surface, and you want to figure out what is the integral over the solid angle that gets you to this surface of cosine of theta, right? That's going to be the contribution to Fij. So basically what you want to do is, here is the unit sphere, and you're projecting this polygon onto the unit sphere. I didn't draw this very well, but you're going to get some kind of a spherical polygon here. Something like that, right? Where this projects on the unit sphere. And my claim is that the contribution of this polygon is actually the projection of the polygon onto the plane below the sphere. I got one more side here. Okay, so these are going to be great circle arcs on the sphere, right? Because they're intersection of the sphere with the plane that goes out to one of these edges. So each of those is going to be a great circle arc. And if you have a great circle arc projected, you're actually going to get an arc which is a piece of an ellipse, right? Because you have a circle, but you're projecting it as a slant, because the circle is in a slanted plane. So it's going to turn to an ellipse. So I have two things to prove. First is that the integral over the omega to this polygon P of cosine theta d omega equals the projected area onto the sphere and then onto the plane. Well, the projected area of some little piece of the polygon, dA, into this sphere here is really the d omega, right? We already did that part. So what I have to show is, if you have a little piece of a sphere, then the projection of that vertically onto this plane. So let me take a piece of a sphere, and here's the plane of the equator. Maybe here's my north pole here, and I have a piece of a sphere. I don't know, let's draw it as a d theta here and a d phi there. Let's see what this is going to look like, something like that. So let's see, d theta is going to bring it down like that much. So I want to see what that little piece looks like over here. Did I draw this right? 1, 2, 3. This should go like that. Right? So what are these arcs? This one we said was sine theta, if here's theta. So this arc is sine theta d theta sine theta d phi. And this arc here is d theta. Well, this one is the same here, right? Because it's just, this was a horizontal piece, and that's sine theta d phi. But what is this piece? Well, now we just need a side view. So here is theta, and here's d theta. We have a little piece here. How does it project there? Right? We can just see this projection. This was d theta, and let's see, this is perpendicular, this is, I guess this angle is theta, that means this is 90 degrees, this is theta in here. Right? This side is perpendicular to that side, and this to the normal, and this side is perpendicular to this ray in direction theta. So that means that this one is d theta cosine theta, right? So the ray, this is now d theta cosine theta, and that means this projected area to the big area is cosine theta, right? So since the projection onto the sphere got this thing, and the projection vertically got cosine theta, this is the contribution to the form factor if the polygon was entirely visible. So let's see. I think since it's getting near the end of the period, I have to finish that computation next time. But let me just say what happens if it's not entirely visible. There's something called the Atherton-Weiler visible surface algorithm, which you put in your list of polygons in your database, and what comes out is a list of visible polygons defined by vertices and edges. And the way it's done is, if you have a polygon, projected on a scene, and you have another polygon in front of it, basically, if they intersect, you have to do something special. But if this is another scene polygon that's in front, you basically want the part of this polygon that's outside of this polygon. So basically, if this is counterclockwise, and since it's outside, we'll make this one clockwise. Basically, you go around this polygon, and first of all, you find all the relative intersections of edges of one and the other. And as you go around here, every time you hit an edge of this polygon, you make a left turn, trying to keep the interior to your right, and follow around the edge of the clipping polygon until you hit another intersection, and then you follow around the original polygon. So we can clip polygons against polygons. In fact, even if the polygon has holes, which it will if we have another little triangle in front, we just make those holes go counterclockwise, and you'll get a collection of boundaries that define what's left in terms of, and even if they're inside each other, they all have the interior to the left of the arrow. And so when you're done your polygons in, polygons out visible surface algorithm, you're going to have what part of that polygon is visible, and then I'm going to have to show you next time how you actually compute the area of this piece, and that'll give you the form factor that you could do analytically for point to polygon. Okay, that's it for today.